Last transmission from a spacecraft at the edge of the Kuiper Belt takes over 7 hours to reach Earth. 7 hours at the speed of light. That signal, traveling at 300,000 kilometers per second, still needs the better part of a day to close the gap between you and home. And that's just a radio wave. That's not a rescue ship. That's not a supply run. That's not a way back. That's a whisper crossing a void so deep that by the time anyone hears it, whatever emergency prompted it has already been decided, one way or another. The Kuiper Belt is one of those places that sounds close when you first encounter it. It's in our solar system, after all. Not some distant star, not another galaxy. Just the outer neighborhood, past Neptune, past the familiar planets, a region of frozen rock and ancient ice that's been sitting there since the solar system first coalesced 4.5 billion years ago. We've even sent a spacecraft there. We have photographs. Scientists study it from their offices. It feels knowable, manageable, like something we could reach if we just tried hard enough. But that instinct, that reflexive human confidence, is exactly what makes the Kuiper Belt so deceptive. Because the moment you start converting its distance into human terms, the math stops being astronomy and starts being something closer to a verdict. The inner edge of the Kuiper Belt begins at roughly 30 astronomical units from the Sun. 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. So 30 AU means 4.5 billion kilometers, minimum. The outer edge stretches to around 50 AU, pushing towards 7.5 billion kilometers. These aren't distances between cities, they aren't even distances between continents or planets. They are distances so large that our fastest machines take years to cover them, and our minds genuinely cannot picture them without the hell P of analogy. Here's one that might help. If the distance from Earth to the Moon were the length of a single step, then the distance to the inner Kuiper Belt would be roughly the equivalent of walking from New York to Los Angeles, and back, twice, every day for 2 years. That's not hyperbole, that's the ratio, and yet we dream of sending people there. We do dream of it. That impulse is worth taking seriously because it doesn't come from nowhere. The Kuiper Belt is extraordinary. It's a vast archive of primordial material. The leftover building blocks from the solar system's formation, preserved in deep freeze for billions of years. Pluto lives there. So does Eris, Makemaker, Haumea. Dwarf worlds with their own moons and geological histories. Scientists believe the Kuiper Belt holds clues to how planets form, how water arrived on Earth, maybe even how the ingredients for life get distributed across solar systems. There are researchers who have dedicated their careers to understanding it. The dream of exploring it directly, of sending humans to walk on a Kuiper Belt object and bring back samples, is scientifically compelling. It's not a fantasy born from ignorance, it's born from genuine scientific hunger. But hunger doesn't change physics. New Horizons launched in January 2006. It was given a gravitational assist from Jupiter, one of the most powerful slingshots in the solar system, and it left Earth faster than any spacecraft before it, over 58,000 kilometers per hour. 9.5 years later, in July 2015, it flew past Pluto. Not orbited, not landed. Flew past, at a distance of roughly 12,500 kilometers, snapping photographs in a window that lasted hours. Then it kept going. By 2019, it reached Arakoth, a small contact binary in the Kuiper Belt, over 6.6 billion kilometers from Earth. The total journey, 13 years. New Horizons carries no humans. It has no life support. It doesn't need food, water, medical care, or psychological stability. It doesn't lose bone density. It doesn't develop radiation-induced cataracts. It doesn't grieve. It is a machine, and it still took 13 years to reach the Kuiper Belt's interior. A crewed mission using equivalent propulsion would need to be faster to keep the crew alive long enough to arrive. And we currently have no propulsion system that could accomplish that while also carrying the mass a human crew requires. Chemical rockets, the foundation of every crewed mission in human history, are essentially controlled explosions. They are phenomenally powerful and phenomenally inefficient at the scales we're discussing. The rocket equation, the mathematical relationship between fuel, mass, and velocity, becomes catastrophic at interplanetary distances. The more fuel you need to go faster, the heavier your ship becomes, which means you need more fuel to accelerate that weight, which adds more mass, which demands more fuel. The equation curves against you exponentially. Ion drives are more efficient but generate thrust, measured in millinewtons, barely enough to slowly accelerate an uncrewed probe over years. Nuclear propulsion concepts exist on paper and have for decades, but none have been tested at crewed mission scales, and none solve the fundamental mass problem that haunts every long-duration mission. The Kuiper Belt, under current physics, is not a difficult destination. It is an effectively unreachable one for human bodies. And the body is where things get genuinely grim. Assume for a moment that some future propulsion breakthrough cuts the travel time to 5 years each way. A 10-year round trip. Still longer than any human has ever spent in space by an order of magnitude. The longest continuous stay aboard the International Space Station is just over a year, and the astronauts who complete those missions return to Earth unable to walk without assistance. Their cardiovascular systems have partially reorganized. Their bones have shed density at a rate of 1 to 2% per month, not across the whole skeleton evenly, but concentrated in the load-bearing bones of the legs and spine, precisely the bones you need to function as a human being. After a year, that damage requires months of rehabilitation to partially reverse. After 5 years, the math becomes deeply uncomfortable. Bone loss of that magnitude doesn't just mean fragility. It means your skeleton becomes structurally compromised in ways that no amount of exercise fully prevents. Resistance training in microgravity slows the process, but does not stop it. Your leg bones, after 5 years without gravitational loading, would resemble the bone density of someone in their late 80s. A stumble becomes a fracture. A fracture in deep space, billions of kilometers from a surgical suite, is potentially fatal. The cardiovascular system doesn't wait to start changing either. In microgravity, blood and fluids shift toward the upper body. The heart, detecting what it interprets as increased blood volume, begins shedding cardiac mass. It shrinks. It becomes less efficient. After years in space, the heart returning to gravity faces a profound mismatch between its reduced capacity and the demands of a 1G environment. Astronauts returning from long missions frequently cannot stand without their blood pressure crashing. That's after a year. After 5, the reintegration into gravity becomes a medical emergency in itself. Then there's radiation. Earth's magnetic field and atmosphere absorb the vast majority of cosmic radiation before it reaches us. The moment a spacecraft leaves that protection, the crew is bathed in a constant stream of galactic cosmic rays, high-energy particles that pass through spacecraft walls, through flesh, through DNA. Solar particle events can spike that exposure dramatically in hours. The ISS, still within the partial protection of Earth's magnetosphere, already delivers radiation doses that approach lifetime safety limits for year-long missions. In deep space, past Jupiter, past Saturn, past Neptune, past the heliopause, there is no shelter. The DNA damage accumulates. Cancer risk climbs. The central nervous system is particularly vulnerable to high-energy particles, and studies on rodents exposed to simulated galactic sea. Cosmic ray environments have shown measurable cognitive impairment, disruption to memory, decision-making, and anxiety regulation. You are not just physically deteriorating on this mission. You are, in a very real neurological sense, becoming less capable of running it. The cascading nature of these failures is what makes the Kuiper Belt specifically so unforgiving. It's not one problem. It's a system of problems that amplify each other. Radiation weakens the immune system, meaning infections that would be minor on Earth become serious threats in isolation. Muscle atrophy reduces the crew's ability to perform physical repairs. Cognitive impairment affects judgment. Communication delays, over 7 hours one way at Kuiper Belt distances, mean that any crisis must be solved by the crew alone, in real time, with degraded bodies and minds, using equipment that has been operating for years in an environment that is hostile to every material it's made from. Micrometeorite impacts are low probability but non-zero over a decade-long mission. Mechanical failures compound, spare parts run out, there is no resupply, there is no rescue. The trap is not dramatic, it is quiet and statistical and absolute. With current technology, and with any technology that exists or is in credible development today, a crewed mission to the Kuiper Belt is not a challenge waiting for more funding. It is a closed door. The distance alone pushes travel time into ranges that destroy the biological systems we'd need to survive arrival. The propulsion needed to shorten that time to survivable ranges doesn't exist. And even if it did, the radiation environment of the outer solar system would require shielding masses that no realistic launch vehicle could carry. These are not engineering problems. They are confrontations with physics and biology that do not negotiate. And yet, we've been there. Not with hands or eyes, but with mathematics and machinery. New Horizons sent back images of Pluto's heart-shaped nitrogen ice plain, a feature so unexpected it rewrote theories about geological activity in the outer solar system. It showed us Arakoth, a contact binary that formed in the earliest days of the solar system, pristine and ancient and strange. Voyager 1 crossed through the Kuiper Belt and kept going, now drifting through interstellar space, still transmitting after nearly 5 decades. We built things that could make the journey even when we couldn't. That is not nothing. That is, in its own way, extraordinary. We may never stand on a Kuiper Belt object. We may never feel the silence of that frozen wilderness with our own senses. But we mapped it. We named its worlds. We understand its chemistry. We sent our machines as proxies for our curiosity, and they reported back faithfully across billions of kilometers. The cosmos does not owe us access. It simply exists, indifferent and vast, and we are the only things in it known to look outward and wonder. That capacity, to understand a place we can never visit, might be the most remarkable thing about us.